All right. So let's talk about Tectonic Manifesto Concept 12. This is where we ended. The changes in tectonic style will affect other planetary systems. Now, we haven't talked much about emergence, and we're not going to, but emergence is something that I'm very interested in. I encourage you to go to YouTube, Google it, and and look at emergence. It's not a theory. Emergent systems. There's some very nice videos there. But what we want to emergence is the property of any high energy, far from equilibrium system like the Earth, right? Because at the surface we're basically at 25 degrees centigrade. At the core it's hotter than the surface of the sun. Very high energy, very far from equilibrium system. And Earth and other active silicate bodies are emergent systems. And because they are emergent systems, the tectonic behavior of these active silicate bodies are likely to change through time. For example, from one style of single lid behavior to another, and or from a single lid to plate tectonics and vice versa. And these tectonic transitions are likely to take many millions of years to accomplish, but they will, in the process, profoundly disrupt the surface environment, the composition of the atmosphere, the body's rotation axis, and many, many other planetary characteristics. So you've seen part of this diagram before, where we go from magma ocean to a dead body like the moon, with stagnant lid, you know, volcanic heat pipe like Io, Venus's thin lithosphere, lots of plumes and rifts, and then it can go out of a single lid to plate tectonics like Earth has today, and then it could go straight from this to this. That Mars shows no evidence of, well, not really. It may be a little bit of evidence of having plate tectonics, but this is sort of a conceptual idea of what a silicate body would do as it evolved from the beginning 4.5 billion years ago. The present, it could, evolve to a Venus-like single lid situation or plate tectonics, or it could go dead depending on size. This is a very exciting field to me, the tectonic evolution. And we'll cover this, part of it at least, at the end of the class when I talk about the evolution of plate tectonics. All right, Tectonic Manifesto Concept number 13. Changes in tectonic style cannot be predicted in any detail. All right, they can be reconstructed by in looking at the historical record, but they cannot be predicted because of the nature of the high energy, far from equilibrium emergent systems. Future tectonic styles of an active silicate body cannot be predicted in any detail. Tectonic mode switching, going from, say, single lid to plate tectonics, is likely as a body cools down or more rarely heats up. However, the tectonic history of an active silicate body can be reconstructed to some extent using geologic techniques if the rock record is preserved. So identifying what are the diagnostic indicators of different tectonic environments, different tectonic styles, finding evidence for these in the rock record is required to do that, to reconstruct the system. All types of evidence are useful in this effort, but the large-scale evidence, diagnostic rock assemblages such as ophiolites and blue schist, provides more compelling evidence than small-scale evidence like trace elements or isotopes, because small-scale evidence can be due to many different kinds of changes in tectonic style. For example, from one kind of single lid to another, whereas large-scale evidence provides more information, for example, PT environments, which are characteristic of tectonic environments. For the foreseeable future, reconstructing a silicate body's tectonic history will only be possible for Earth, with efforts for the Moon and Mars to follow. Okay, there's a mouthful there, but I think you get the gist that nobody can really tell you when plate tectonics will stop and what the next tectonic style will be in any detail. Tectonic Manifesto Concept 14. We are just beginning. Oh, Clint's got a question. Clint, fire away.
Yes, this is similar to, when there's a balanced rock somewhere and somebody asks, when's that rock going to fall? And you say, well, I don't know, but when it does.
Yeah. Yes, that is an example of and people love to predict the future. This is a favorite human activity, not limited to geology. And anyway, I digress. But yes, we're just beginning to learn about planetary tectonic style. So the concepts and guidelines articulated above will surely need to be modified as we learn more about silicate exoplanets. So we're, exoplanets are a big thing. And here's a few examples that we can imagine might exist, but we have no evidence that they do. So number one, exoplanets with a high surface temperatures. These include magma worlds, which don't have lithospheres and can't have tectonics until lithosphere forms, because according to my definition, which I think is useful, lithosphere tectonics happens in the lithosphere. So if you don't have lithosphere, you don't have tectonics. You have something else. B, silicate exoplanets with surface temperatures greater than 1,000 Kelvin. So at this temperature, so that's like, what is that? 800, 700 degrees centigrade. At that temperature, surface rocks are deformable and such bodies might not have much of a lithosphere. Do these have tectonics? We don't know because we haven't got any to study yet. C, tidally locked exoplanets. So these can be hot, even molten on one side, but cold on the other. So each hemisphere would have a different tectonic style. Now, Mercury is tidally locked around the sun. Our moon is tidally locked around us. I believe Io is tidally locked around Jupiter, but Mercury is a dead planet, so it doesn't have any tectonics. So, it can't have this. But we're talking about tidally locked active silicate exoplanets, which could be molten on one side, but cold on the other. So you can imagine a tidally locked active exoplanet that had a stagnant lid on the cold side and a magma ocean on the hot side. It's imaginable, but whether or not it happens, who the hell knows? And then finally, very large silicate exoplanets, things that are much larger than the silicate bodies that are much larger than the size of Earth. Here, a asthenosphere can exist at higher pressures than the neutral buoyancy depth of partial melt. Okay, so what does that mean? So on the Earth, that because magma is more compressible than rock, there's a certain pressure at which magma is denser than the rock that hosts it. So it will sink. And at shallower depths, lower pressures, it will rise. And that's the situation for Earth. Earth's magma comes mostly from the asthenosphere, which is a few hundred kilometers down, well below the pressure of neutral buoyancy. But in a super large silicate body, that might not be the case. But nevertheless, such bodies may have an outer layer that shows brittle behavior that could represent lithosphere. So let me see, do I have one more? Yes, and finally, Tectonic Manifesto Concept 15. Tectonic style has a big influence on other planetary systems. Global tectonic style has a strong effect on planetary degassing, ingassing, atmospheric composition, climate, and therefore for life emergence and evolution. And in planetary history, major changes in global tectonics are likely to be associated with major changes in atmosphere, climate, landscape, and life. And that has been a fair amount of my research in the last few years. Okay, so I hope you found that sort of review of the Tectonic Manifesto, which was basically a thought piece that is free for download and is also you will see in the e-learning that there's a folder called Those Who Want to Learn More. What I'm doing is populating that with the papers that are in the syllabus that I've suggested, and also a few more that aren't in the syllabus. But certainly the Tectonic Manifesto is in there. So take a look if you're interested. All right. So let's move on and talk a little bit more about these concepts, and particularly what the bodies of our solar system tell us about tectonics. So number one, large, mature planets have either single lid or plate tectonics. So these are ones that are active, right? The large silicate bodies are still active. The small ones they cooled so fast, they're basically just rocks in space. Whereas Earth and Venus, to a certain extent, Mars, certainly Io, these are very vigorous convecting silicate bodies. So there's two styles of tectonics, and there's single lid, which I've talked about, and then there's plate tectonics. Single lid is unbroken lithosphere encasing the entire planet. And we could talk about active single lid and dead single lid or stagnant lid. And you may, if you read the literature, you'll see that other people refer to all single lid as stagnant lid, and I'm kind of isolated in talking about single lid as the active end member of non-plate tectonic silicate bodies, and reserving stagnant lid for dead bodies like the moon or Mercury. Okay, active single lid bodies, the mantle generates magma, which erupts as lava, right? Venus and Mars both have that. Dead single lid, the mantle can't melt to generate magma, and Mercury and the moon are good examples. And then we have plate tectonics. And in plate tectonics, the lithosphere is fragmented and the fragments move independently. Interesting. So we'll just take another last look at this sequence of sort of the cooling of a silicate body. Sort of, this is a conceptual diagram. We start off with magma ocean. We don't know how far down that existed. Okay, so it's a fairly complicated diagram. So up here is lithospheric thickness and strength going from none to very, very thick. So the lithosphere, through this progression from the beginning of a planet silicate body to its death, the lithosphere is thickening. And you can see that here, right? No lithosphere. That's got basaltic crust, but no mantle lithosphere. There we see the mantle lithosphere, that dark green. Here the mantle lithosphere is getting thicker. And at the end, terminal stagnant lid, the lithosphere extends all the way to the core, or deep enough that the effects of whatever convection might be going on above it are completely unaffecting the surface. And then somewhere between this style and this style, we have the opportunity where we have lithosphere that's thick enough, dense enough, strong enough to sink in subduction zones, and we can have plate tectonics. Now, this is different than a lot of other geoscientists. That's why it's not on the test. I'm not going to test you on my ideas. I'm going to test you what's in the book, because I want you to read that book, and I want you to read it carefully. But this is material that is I think thought-provoking, and I think useful. And space is such a big part of our lives nowadays that everybody's interested in space, and geologists should be too, because we can learn lessons from these planets. And what you can see here is this sequence is very much dependent on what we learned about Io, Jupiter's moon, what we learned about Venus, what we learned about Mars, and what we've learned about the moon and Mercury, and of course the Earth, this is going to be our course. We're going to focus on this. The book focuses on this. Okay. So this is sort of a conceptual framework for you to understand the role of lithosphere and the unusualness of plate tectonics, the remarkableness of plate tectonics. Any questions on this diagram? All right. Now, Tectonics concerns deformation of the lithosphere. And as I have said before, and I hope if there's one thing, and I will remind, oops, we have a question.
Yeah, I was just curious, is Mars still active today?
Yes, in my opinion, it is. So number one reason is those volcanoes look young. They're not. We've been observing the surface of Mars for about 50 years. We have never seen a volcano erupt on Mars, and but nevertheless, the form of those volcanoes is so youthful. Number two, they sent a instrument package to the surface. It's called InSight a few years back, and it was listening for seismic signals. So uh, dead planets have seismic signals too, like the moon, but its seismicity is related because we sent a package up there with the Apollo program. Its seismicity is either very shallow, related to impacts, or very deep, related to contraction and movement around the core mantle boundary. Whereas, as we learn in this course, Earth's seismicity and that of other active silicate bodies is deeper than just the surface impacts, but not very deep. And that's Dr. Ferguson, who's our geophysicist, and I have been working on a study. It basically compares the seismic activity through this sequence because we have seismic data, certainly from Earth, seismic data from the moon, and seismic data from Mars. So if you look at this, we've got this story, we've got this story, and we've got this story from seismicity. So it makes a nice comparison. And maybe sometime we'll ask him, maybe I'll see if he wants to talk to one of our open times, if there's interest. All right, so these are the 5 possible stages in the tectonic evolution of a big enough silicate planet, right? So, if you're not very big, you're never going to really get out of this stage. The body will cool completely, and that's basically over at the beginning. But if you're big enough, you might evolve like this, right? From magma ocean to heat pipe, through drips and plumes, delaminations and upwellings, and finally to plate tectonics. That's possible. Doesn't mean it happens, but it's emphasizing the role of the lithosphere in controlling tectonic style, which is a point you'll hear over and over again. All right, so let's look at some Earth-like planets and moons. So we talked about the tectonic activity index, from 0 to 1 being characterizing small dead ones like the moon and Mercury. And there's medium-sized, almost dead one, Mars, which has a tectonic activity index of 2. The reason it got 2 is it seems to have volcanic activity. It seems to have deformation, surface deformation, but it's also densely cratered in the southern hemisphere. So you can't ignore that. Then we have the large active ones, the largest and the most active of Earth and Venus, which have tectonic activity indexes of 3. All of them started hot about 4.5 billion years ago, but the smaller ones cooled faster and died. So the number one, the early bodies were heated by more radioactive decay, and this is only considering the existing radioactive elements that we have on the Earth today: potassium-40, uranium-235 and 238, and thorium-232. And just considering those and extrapolating them back in time, whereas today this radioactivity is generating on the order of 20 terawatts due to radioactive decay. At the beginning, they were generating on the order of 100, 5 times as much. And in addition, at that time, there were also a lot of very short-lived radioactive isotopes like aluminum-26. So these short-lived radioisotopes like plutonium, aluminum-26, there's a bunch of them. They inject a tremendous amount of heat into the body at the time that they're decaying, but once they're gone, they don't contribute at all. So this magma ocean, the intense heat of the silicate bodies early in the solar system are are thought to have been very, very hot because of this one reason alone. But there are other reasons. So because you had this very hot magma ocean situation, it was easy for the iron nickel in the accreting material to separate from the silicate material and sink. And this sinking converted gravitational energy into heat. And that alone is thought to be sufficient to melt the planet, in addition to the radioactivity, just the core formation. And that would have, so this intense melting is thought to not only allow the core to form, but it also would allow the lighter elements like silicon and potassium, things like that, to form a primitive crust, which is shown here as anorthositic, which is basically a very plagioclase-rich, feldspar-rich crust. And that comes from studies of the moon. The reason the moon is white is because of plagioclase, an early anorthositic crust. Earth does not have any evidence. We certainly must have had a primitive crust, but none of it is preserved. The oldest rock formed 500 million years after the Earth formed. So it seems that this primitive crust was completely recycled. A third reason that at least one silicate body was hot was because of the major impact. So there is the impact of a Mars-sized object called Theia about 4.5 billion years ago during the early accretion of Earth. And this impact was enough to cause Earth to melt completely. And the moon is thought to have formed from the debris that was thrown out of the Earth due to this impact. So that's the third reason that at least Earth would have been completely molten. And this is sort of a cartoon. Here's Theia, here's the Earth. That's the core, that's the mantle. There's the impact. It's thought that, that most of the Theia's core joined Earth's core. This lot of material was, we have a question. Go ahead,
Yes,
Clint.
and remember when you were talking about the densities of silicate bodies as a whole, and the moon is unusually light, but it is a lot like the upper layers of Earth, which
Yes.
was one of the hints that of why people think this.
Yeah, and it's got a small core. We know that from the geophysics experiments they did with Apollo. All right, so this magma ocean stage probably in years, and it was obviously very early in the life of the silicate planet. Now Earth has been cooling. We know this because we can reconstruct the temperature of magmas from ancient basalts. These are 3 studies in here, one of them in blue dots, one of them in bars, and one of them is this yellow region. So you can see this magma ocean would have happened if the Earth's what we call the mantle potential temperature. We don't need to go into that, but it basically means that the temperature of Earth's mantle at a certain depth. So at 1800 degrees, we had magma ocean. We can reconstruct the temperatures of these basalts and this unusual class of lavas called komatiites. So and then we can carry that down into younger times. So today the mantle potential temperature is about 1350. We argue about it, but that's cooled quite a bit from on the order of 1800 degrees that existed at the beginning. Let's look at some dead bodies. So how can we tell they're dead? Well, lots of impact craters and no evidence of recent igneous and tectonic activity. So Earth's, we've talked about the moon being a tectonically dead body. Well, we could call it, I like to call them planetoids, right? Because planets go around the sun, moons go around the planet, but from the point of view of the geologist, it doesn't matter whether they're a moon or a planet. We're still interested in what they can tell us about how silicate bodies evolve. But here you can see, you see lots of these impact craters, and there's so many impact craters that if another impact happens, it'll partly cover another one. We can call this a saturated surface. Okay, so it's pretty easy to tell dead bodies. And this is the Chinese are starting to go up there. This was a view of the surface of a moon from the Chinese rover in 2013, Jade Rabbit. And our moon preserves an early planetary history. So there's two kinds of crust that we see on the moon. One is the highlands, these white areas, and the other are the maria. And that's Latin for ocean. And that's because the early astronomers looked at it and goes, oh, that must be an ocean. We'll call it a mare imbrium. They're obviously not oceans, but they are basically regions where there's large regions covered by basalt. These are flood basalts. So, the lunar the highlands are older, in the order of 4 to 4.5 billion years, 4.4. The maria are younger. They're range in age from 4 to 3.2. Recently, the Chinese landed in a different one and brought back samples, and they have a significantly younger age, which was maybe 2 billion years. So this needs to be modified. But the point is that both the highlands and the maria are not active anymore. The highlands are much more impacted, telling us they're much older. And the maria are basically big flood basalts covering large areas. Okay, so this is kind of how we think the moon fractionated early. So there was an early magma ocean, and then as that cooled, these minerals crystallized: feldspar, olivine, and pyroxene. You guys are all familiar with those. And in an iron-rich magma, which is what this was evolved to be, the feldspar is light enough to float. So it would make a scum on the magma ocean, whereas the olivine and pyroxene are dense and they would sink, right? So the age of the lunar highlands has been dated by these scientists to be 4.44 billion years. That's easy to remember too, 4.44, but significantly younger than 4.56, 100 million years or so. All right, so how far along in tectonic evolution did the moon get? Maybe to drips and plumes. Maybe that's what we're seeing. The mare are these plumes and but it never got farther than that. So these lunar maria are the moon's last tectonic gas. It's interesting that the maria are all concentrated on the side facing the Earth, and the other side, the far side, has got almost none of these large ones, and very few spots of a little bit of it. Interesting. We don't really understand why. So impact craters on the moon. There's the youngest one. This is called Tycho, and you can see that the rays coming out of it, basically ejecta from this impact. And these meteorite impacts are basically sweeping up all of the solar system's detritus by growing planets. And that there was a lot of detritus early on, and there's hardly any now. This is interesting. This is a remote sensing image of iron content. And anorthosites are very low in iron, and basalts have a lot of iron. So this is basically mapping the lunar maria, right? You can see the areas of lunar maria and a little bit, of these basalts on the other side. It's kind of interesting stuff that's coming out of space sciences now. Well, that's actually quite old. All right, Mercury is the smallest of the inner rocky planets, and its story is very much like the moon's. What's interesting is how big its core is. So its core is a much larger fraction of the planet than the Earth's, and it's curious why that should be. That's an area of a lot of people are wondering about that. Now, this is the image of the moon. It's basically, I'm sorry, image of Mercury. It was imaged by the spacecraft Messenger in 2011. It is also, its surface is saturated with craters, but there's no lunar maria. So that's interesting. There's no maria. There's none of these flood basalt like we have on the moon. What is interesting are these faults. So this is a fault scarp that can be traced all the way across the surface, right? And they seem to have, some of these craters seem to be filled with lava, like that one there. So here's another view of that fault scarp, right? You can see it's disrupting craters. There's some craters that are younger than it, the smaller ones, but the older ones are cut by it. This is called Victoria Rupes. So it's interpreted as a thrust fault, like that. And what is the origin of these thrust faults, which is why Mercury gets a TAI of 1, is because the partial solidification of the core caused internal shrinking and the outer rocky layers had to contract. So we could argue whether that's tectonics or not. I don't think it is. It is in the lithosphere, but it's not reflecting mantle convection. It's sort of a terminal stage. And I think the reason I think most people think the reason the moon doesn't have these thrust faults is because its core is so much smaller than Mercury's. So it's cooling and shrinking had a much smaller effect on the planetary, the overlying layers. Now, another important clue is Mercury's magnetic field. And we're going to talk a fair amount about magnetics, planetary magnetics, Earth magnetics. Mercury's magnetic field has a global magnetic field, which is approximated by a dipole, which means a north and a south rather than a quadrupole or an octopole, meaning there's more than two magnetic poles. And the magnetic field is very weak. It's only about 1% of ours. And the origin of the magnetic field is generally explained by convection in the liquid iron core, which requires that at least some of Mercury's core is molten and is convecting, but not very vigorously. So we can summarize the dead bodies, the moon and Mercury. No magmatic or tectonic activity for billions of years. There's a preservation of the primitive crust, the first crust that formed, and the ancient bombarded surface. There's no evidence of spreading ridges, trenches, or transform faults. And of course, not only no plate tectonics, but no tectonics of any kind. All right, so other planets in our solar system have magnetic fields. But interestingly, Mercury's is stronger than that of Venus or Mars. So we measure the magnetic field strength in nanoteslas and little n big T. Actually, nanoteslas sound like a very small electric car, doesn't it? So here's Earth, 30,000 to 60,000 nanoteslas, stronger at the poles, weaker at the equator. And here we can say, okay, is that the highest in the solar system? No. Jupiter's magnetic field is 20,000 times stronger than Earth's. Saturn's is 500 times stronger than Earth. Uranus is 40 times stronger than Earth. Neptune, interesting, is only a quarter of that of Earth. And then we look at the other silicate bodies, Mars, Mercury, and Venus. Mercury is 100 times weaker than Earth, Venus is 25,000 times weaker than Earth. It has almost no magnetic field. And Mars is 5,000 times weaker than Earth. So these magnetic fields are telling us something about what's going on in the core, right? Or so we think. All right, so let's talk about Venus. Venus is a tectonically active planet about the size of Earth. Before we did this mission, we expected that it would have plate tectonics because, when you look for things that you're familiar with, and we couldn't imagine a body the size of us that didn't have a tectonic style like us.
One hand up.
Oh, go for it. Yeah.
Yeah.
Thank you.
And one of the earliest features recognized, I think maybe in the late 70s or early 80s, was uh, some compressional mountains way up in the north side, known as the Maxwell Montes, and people said, "Ooh, wow, look, it looks just like Earth. There must be Earth-like things going on." Which, yeah, in a sense, sort of, but maybe no.
Yeah. Okay. So the question might be, does Venus have plate tectonics? So it's almost Earth's twin. It's about 82% of the mass of the Earth. It's got a surface temperature of 480 degrees centigrade, which is very high. And there have been many missions to it and around it by the United States and Russia and the Soviet Union. But, it's hidden by this dense CO2 rich atmosphere, 90 times Earth's atmosphere. So Venusian topography consists of vast plains covered by lava flows and mountains or highland regions deformed by geologic activity. We mentioned Maxwell Montes and Ishtar Terra. All of the features on Venus are named after women. Um, uh, Venus is scarred by quite a few impact craters, but it's not saturated. Volcanic features dominate the surface of Venus. At least 85% of its surface is covered by lava flows, huge lava flows extending for hundreds of kilometers, more than 100,000 small shield volcanoes. And its surface is thought to be relatively young, and it appears to have been completely resurfaced 300 to 500 million years ago. So this is a topographic map of Venus. Yellows and reds are high regions. Clint was talking about this region. And then low regions are blue. And you can see none of the systematic distribution of highs and lows that you see on Earth here. But very interesting planet, but definitely a single lid planet. So Venus volcanology. There's giant calderas more than 100 kilometers in diameter, and usually terrestrial calderas are much smaller. There is a thing called corona, which we'll talk about a bit more, which we've never described corona on Earth. These seem to be unique to Venus and maybe Mars. These are large circular to oval features encircled with cliffs that are hundreds of kilometers across. They are thought to be the surface expressions of mantle upwelling. And related to corona are called arachnoids. These are also circular to elongated features, similar to corona, but they have sort of things, probably dikes extending out from them that makes them look like spiders. We'll talk more about these. So the Soviet Union landed on Venus and took pictures of its surface 3 times. In 1975 with Venera 9 and 10, and in 1982 with Venera 13, where you got color. It didn't, the landers didn't last very long because of these tremendous temperatures. Electronics will fail very quickly at temperatures like that. So basically they send it down there, they get a few pictures, get a few other things, and the thing is dead. So that doesn't encourage landers. Clint?
Yeah. So I looked up those missions, and more or less it's a titanium ball with some stuff in it. And I don't think it even, you couldn't have parachutes in the atmosphere there. And I don't even think they had retro rockets. I think they just sort of dropped it in the atmosphere. It just sank because the atmosphere is so dense and
Well,
sort of
we
floored.
would have to, that's a whole separate issue of how the Soviets landed
Yeah, I
these
know,
things.
but it's part of the issue of like, how do you find out about this and take pictures of it? And getting there is it's a big problem.
Yeah, no, it was a tremendous success. Now, this is the Magellan image. So this is called imaging radar. And basically you're sending radar down, bouncing it off the surface, collecting it, and using it to develop an image, a map of the solid surface, the reflective solid surface. And Magellan did this imaging in between 1989 and 1994 and generated this map. So 98% of the Venusian surface was mapped by Magellan using imaging radar and then, as we said, blues are low areas and reds are high areas. And you can see very few impact craters. It's been recently resurfaced, and that's consistent with an active silicate body. Okay, they've counted 842 impact craters on Venus. This is a radar image. So this is called radar bright region, these white areas, and these are radar dark. So if you think about how radar works, the rougher the surface, the more it's going to reflect back to the spacecraft, the radar energy. The flatter the surface, the more of it's going to reflect away from the spacecraft. So where you get a lot of reflections back to the spacecraft, rough areas, you will get these bright things. So you can imagine an impact would send out a lot of ejecta. You can see the ejecta blanket coming away from this impact. Whereas lava plains would be relatively flat. And that's out here, and looks like there's some lava filled the interior of the crater too. Now, some of these impacts seem to have triggered eruptions. So here's the impact site, and here's a lava flow that was traced away from it. It seems like this impact allowed magma to come up along the rings and then flow out. And then there's some impact craters that have been buried by lava flows. So here we've got an impact crater, and it looks like it's been completely filled in with lava, or almost completely. It's an example of resurfacing, as you expect on an active silicate body. There's some volcanoes that look like this. This is called, the scientists have called these anemones because of these pedal-like lava flows and radiating radar bright patterns. This is 40 by 60. This is an Earth analog. This is a radar image of Erta Ale in the Afar Rift of Northeast Ethiopia. We'll talk about tectonics of the East African Rift in Ethiopia later. But it basically, you've got some kind of a rift that allows the magma to come out, and it spills out and flows out like that. You sort of get that same impression with this Venusian anemone. Lots of small volcanic cones. So these are the ones in this cluster, about 2 kilometers in diameter, a couple hundred meters high, with 12-degree slopes. And some of them are cut by these younger fractures, right? You see lots of evidence of igneous activity and tectonic deformation, as you would expect for an active silicate body. And then there's some of these pancake volcanoes. These domes are about 25 kilometers across, they reach heights of 750 meters. This characteristic looks like felsic or very viscous lava coming out of the ground. And that's expected for very high silica magmas. So these things are thought to not be basalts, which are low silica. These are thought to be some kind of a rhyolitic magma, high silica. Now let's talk about, oh yes, go
Real
for it.
quick question. Has anybody done an iron analysis of the surface that might show the different composition of these guys?
No, because the The part of the infrared, the part of the spectrum that is sensitive to chemicals, that's in the ultraviolet.
Yeah, I know that
And you
Magellan didn't
can't
do it, but
you can't penetrate ultraviolet through at dense atmosphere.
oh,
That's why we don't all have skin cancer, is because our atmosphere is dense enough to block out ultraviolet. Yeah.
Yeah, I'm just it follows up a little bit on Clint, but I mean, it seems to me like Venus is almost about the same size as Earth. It's closer to the sun, so it's warmer. It's got about the same density, I think, as Earth. So I'm a little confused why it wouldn't have an inner molten core that would create a magnetic field.
Well, one of the reasons is Venus is not rotating as fast as Earth. It's rotating hardly at all and in the opposite direction. So some people have argued that that indicates that maybe it was captured. I think, who was the guy? Velikovsky was talking about Venus being captured from some somewhere else. We don't think that that is true because it sits right about where it should. But yeah, there's a whole literature about why Venus doesn't have much of a magnetic field. And I mean, these are all potential topics for your papers, right? And there's a lot of things I've covered that one of you might go, I want to dig into that more for my presentation, but you don't have to decide that now. So let's talk about corona. So here is one. This is a radar image. So again, the white areas are areas of high radar backscatter. These are steep areas, rough areas, and the dark areas are areas where it's relatively smooth. So the radar is being reflected away from the spacecraft. So what you can see is it looks like this area is relatively flat, and then this is some kind of a steep area, which we know topographically to be sort of a cliff. And then in the interior, it's mostly flat, but there's a lot of reflective stuff that looks like maybe those are lava flows. So these are immense circular to oblong structures, generally 200 to 250 kilometers across, some as large as 1,100 kilometers. Right now, these appear to be unique to Venus, although I'll make the case, if we have that much time, that there might be some on Mars. They have a positive topographic expressions with a surrounding moat or trough, typically stand 2 kilometers above the surrounding plains. Their interiors can be either dome-shaped or bowl-shaped, further characterized by closely spaced ring-shaped ridges, partially closed fractures, or radial fractures. And the interiors of most corona contain numerous small volcanoes. This is the Bahet corona. That's one example of a corona. Now, here are some topographic profiles across the Venusian corona. So it goes, this is a table that these scientists put up. So this is a topographic profile, and these are sort of fractures, faults. So here's one with a dome, here's one with a plateau, here's one with a rim surrounding an interior high, here's one with a rim surrounding an interior dome, here's a rim surrounding a depression, here's one that's more complicated, outer rise, trough, inner, right? So there's a very wide range of morphologies and cross-section. Makes them very interesting. This is an arachnoid. So this is like a corona, but it's got things extending from it that look like spiders' legs. So, that relationship between corona and arachnoids, I mean, if you're a Venusian expert, you can see the difference. To us that are just sort of getting our brains around these unique features, they kind of look similar. They're 50 to 230 kilometers across. They're similar to, but smaller than corona. And the radar bright lines that are extending in many kilometers are thought to be possibly pushed up dikes, intrusive linear features that reach the surface and are somehow pushed up. So here's an arachnoid image, and here's the interpretation, right? So This is thought to be, grabens and lava flows coming out of it. And the Venusian tectonics is captured here. Now we're looking cross-section of the planet. We're sort of looking at the mantle, the core mantle boundary. This is the crust and lithosphere, right? So the blue is the crust, and the dark blue is the crust. The light blue is the lithosphere. In this interpretation, this is sort of showing it in ancient past. Now, this is a conceptual diagram. It's thought to have a thicker lithosphere today, obviously because it cooled, with a lot of mantle plumes. That's a mantle plume extending from the core mantle boundary. And then if material's moving up, there has to be some moving down. So the idea is that this looks kind of almost like a subduction zone, but it's not. It's the crust is not involved. It's just the lithosphere that seems to be sinking like a drip or something, but definitely with convecting mantle. Now, so Venus is Earth's twin, but no plate tectonics. Now let's talk about the sort of when we get the similar kind of tectonic realm, but with thicker lithosphere. Let's talk about Mars. So Mars is in the news a lot, and it's amazing. I really like these two pictures because it sort of reminds us that we're usually wrong, but we make these small advances that are partly right. So this was Lowell's 1906 image from the I think Mount Wilson telescope, just studying it as best he could. And this sort of was the figure that launched a thousand science fiction. So he's interpreting these linear features as canals. And as we know, canals require some kind of an intelligent creature to cut them. So that interpretation by a scientist that there were canals on Mars made people go, oh, there must be people on Mars. There must be Martians. And, the entire realm of science fiction, Star Wars, Battlestar Galactica, whatever the latest, interstellar conflict of civilizations might be, can all be traced back to this sketch, right? This is the sketch that triggered the imaginations of hundreds, if not thousands, of humans to write about things. Now, the image on the right is from Viking, 1976, almost 50 years ago, but you can see that, his canals don't exist. This feature, right, is the Valles Marineris, this rift system. So a lot of what he saw was completely imaginary, right? You stare at a dot in the sky long enough, you're going to see stuff that isn't there. But this is the map we have of Mars topography today. So this is elevation. And what you see here is you've got a northern lowlands, which isn't very densely cratered. You can see a few impacts, and there's many that are much smaller. But the southern highlands, right, it is high, has got much bigger and many more craters. Like that's a big one. These almost remind you of the big ones that are associated with the lunar Maria. And then we've got the volcanoes, right? Olympus Mons and several others, one over here. And we've got this Valles Marineris, this Grand Canyon of Mars, which is quite different than the Grand Canyon because the Grand Canyon was carved by a river. This is completely tectonic. So we've got this really remarkable image of Mars. And so we could talk about Mars having a hemispheric dichotomy. So the southern highlands, densely cratered, Northern lowlands, very little cratering by comparison. And the volcanic features in these black regions and over here, these are restricted to this area sort of in between. And then there's the Valles Marineris. Martian has impact craters. Some of them are quite interesting, and some of them retain evidence of ejecta blancas with prominent lobes. This is something we don't see on the moon, right? Rather than rays showing that dry material was thrown out, this looks like it was mobilized by vaporizing or fluidizing the underlying ice, allowing it to flow away from the impact. So the Valles Marineris Rift, this is the greatest depression known in the solar system. It extends nearly 4,000 kilometers, close to the width of the 48 contiguous United States, and is 2 to 7 kilometers deep. It's a very complex graben system, and you can see, there's the main axis. This is another axis. And this structure is radial to the Tharsis Bulge. This is called the Tharsis Bulge, which is where the volcanoes are, maybe the site of a big upwelling hotspot, mantle plume. This is some of the structures. It was not cut by flowing water, as we said, but there is evidence of erosion. So here you can see evidence of erosion, right? These canyons have got to be cut by water, but this larger structure was not. There's other evidence for extension on Mars, these sets of close-spaced parallel grabens, and there's fractured terrains. That also looks like extension, tectonic extension. So we can see this hemispheric dichotomy very clearly in these maps.
I'm just curious, as far as the erosion goes, wouldn't it also be affected by the storms, like wind, dust storms, and stuff like that, not just previous water?
No, this is a quasi-dendritic pattern that wind is incapable of making. Certainly, there's wind erosion. There's plenty of ventifacts but those are not large-scale features. This kind of a dendritic pattern requires some kind of liquid flowing over a solid surface. So if we look at the surface of Titan is a hydrocarbon moon of Saturn. It might have dendritic patterns, but it's not flowing water. It is flowing hydrocarbons over solid hydrocarbons. But that's an interesting problem in itself. So this is a map of Mars crustal thickness from orbital gravity. Very thin between the Hellas Basin and some of these regions. But overall, this region in the north is thinner crust, 20 to 30 kilometers, according to this. And the highlands are thicker crust, 50 to 60 kilometers. Now, this is something we'll see again when we talk about the Earth. When we see areas of high elevation, that's telling us that the crust is thick. That's got to do with isostasy and gravity. We'll talk about those things. This is not plate tectonics. It's simply the distribution of mass on a body in gravitational equilibrium, which Mars is. Now, where we've been sending our landers, so Viking went up here. The engineers sort of control. They said, we want a flat area for these landers because we don't want them to get on a rough surface where they might tip over. And as a result, this was, these first landers were very exciting in that they gave us information about A, that there were no creatures strolling by to take a look at the lander, and B, the composition of the atmosphere and some very interesting results that have been very useful. So back then, the United States was sufficiently lacking confident that it would send up 2 landers in the hopes that one of them would make it. Now the technology is advanced that we only send up 1 at a time. So, you can sort of go here. Let's see, back after 1976, we didn't send anything to Mars until 1997, Pathfinder Sojourner, right there near the boundary of the lowlands and the highlands. And then we sent Opportunity here in the highlands. And then Phoenix, which was a failure. Spirit and Opportunity were sent at the same time because we were still like, we're not sure we can get 1 there, so let's send 2. And then after that, we started doing just 1. Curiosity in 2012, and my misspelled Perseverance in 2021 up here. And the interest has been in, focusing on this boundary between the highlands and the lowlands. And the Perseverance stories that are still coming out are very interesting. Now, this is how we see, or somebody sees, the mantle convection, that what we've got are these bulges, these few bulges and few large volcanoes are built above a few large mantle plumes. Some people have argued that maybe there once was something like seafloor spreading, because we've got these magnetic anomalies. And we'll talk about magnetic anomalies on the Earth because these are very important clues. They were maybe the most important clue about seafloor spreading was identifying and understanding what the significance of Earth's ocean magnetic anomalies were. And here you can see the orbital magnetic mapping suggesting some very large wavelength anomalies over very large areas. They don't look like Earth magnetic anomalies because Earth's magnetic anomalies are much narrower than these. These are hugely wide, but they are definitely there. So Earth has plate tectonics, and here is one encapsulation of it, and we'll be examining the Earth in much greater detail in the rest of this course. You can see the plate boundaries where the plates pull apart, and you can see the velocities in centimeters per year, and you can see places where the oceanic plates are being subducted, and we can see collision zones through here, and the full range of tectonic styles that characterize Earth are to a certain extent captured by this map. And we have to ask, why only us? I mean, Earth is over and over and over and over special. It's the only planet we know of with life. There's all kinds of things that are unusual about it among the silicate bodies. It's the only body with significant amount of surface water. And then we have plate tectonics. It's the only body that we know of with plate tectonics. I mean, the more you learn about the Earth and the more you put it in this setting of the solar system, the more special it appears to be. And the rest of this course, we're going to focus on Earth's specialness. I think that's me. I think I've done. Oh, no, not quite. Just to make this point about Earth being an active body, we don't have to ask, we don't have to really go, why do we know that? But one of the characteristics of active silicate bodies is they don't preserve their impact craters very well. And this is the map of 182 known impact structures on Earth. You'll notice not very many in equatorial Africa or Amazon or the tropical regions, because they're just erased by erosion and grown over, and you just can't see them anymore. You want them in deserts. Deserts are good places, or where there's a lot of people. They tend to notice them.